All right, you have a stone, it's thrown horizontally at a certain speed, certain height. How far does the stone land from the base of the cliff? The first thing you want to do here is find the time. Think about this, remember? No, you want to find the time that is required for this stone to travel this distance. And then we want to figure out, based on the velocity in the x direction, how far it's going to travel in that time. First find the time, and then find the distance. I'm just going to write the equations over here to remind you what they are. Think about what your components of your velocities are, your Vx and your Vy, and what's being described in the problem. Grace, Tamara, Mason. All right, let's just try to do about 15 more seconds or so. Morning, John. Feel free to ask your neighbor. We're doing pretty well on this. I think most of us have this down, but if you don't, that's okay. We still have some practice. We're going to do some more difficult problems today, too. All right, I'm going to stop at 240. 240. Okay, awesome. B is right. What you want to do here is first find your time. Almost always to find the time, you're going to use what? The x or the y? Almost always, because remember, the time that it's in the air is dependent upon how high it goes up. Sometimes, depending on the information that you have, you might use the x. All right, that doesn't happen very often. But here, we find the t from the y motion. I know, first I like to draw a picture. This thing goes off horizontally and it travels like that. I know that since this is y naught equals 0, that this final position is y equal negative 125. And so I use this to find that. I say negative 125 equals v naught y. Gosh, what is v naught y in this case? It's 0 because the velocity here is only in the x direction. You know that because it says it's thrown horizontally. So it has no y component. It only has an x component. So negative 125 equals 0 times t plus 1/2 of negative 10, that's my acceleration, times t squared. So that works out to be negative 125 over negative 5 equals t squared. That's 25 square root equals t. So t is equal to 5 seconds. And then the next step is to find x. So I use this and I say x equals Vx, which is 10 meters per second. That's just the speed that it's traveling. Remember, no y component, only an x component, times the time, which is 5 seconds. So it's 50 meters. B is the right answer. Okay? Let's try this one. So this is from an old exam. It's similar to what you might see. I'm sorry, it's not a quicker question. Similar to an old exam for your response. I'm going to give you a few minutes and then I'll jump in there, but I want you to get a good start on it. Notice what's given. You have the angle, you have the initial speed, and you have the time that it strikes here. Because you have the time, it makes it a lot easier to work through. So, you want to know the height of the cliff, the speed of the stone just before impact at point A, and then the maximum height H above the ground. Those first two should come pretty quickly. It's going to be simple one-step problem. But you'll first need to find the some of the components of the velocity. So I'll give you a few minutes, and then I'll jump in. I'll walk around. If you're just completely lost, I'll be over and give you a little update. I'm sorry, let's change this one to 2 seconds. Change it to 3 seconds. 3 seconds. You'll see why. Velocity is 30. We'll write our equations down. The first two are pretty basic. So let me just write our equations down. We have y equals v naught y give me the direction on the first part A. How do we find the height of the cliff? What is the height of the cliff? What's the variable that we're looking for? We're looking for y, right? And so I have this expression for y. It's the only one with y in it. Can I use it? Do I know everything here? I do, actually. I can find v naught y. It's just v naught times actually cosine or sine? Sine of theta. I know t. T is given. That makes this problem a lot easier. And I know ay. So part A is is the only step that you have for part A is plugging in the right time. So I have y equals v naught sine theta times t plus 1/2 ay t squared. And so that's equal to, is it equal to 24? Does anybody else confirm that? 24? All right, 24 meters. That's putting in v naught of 30, theta of 50, t of 2, and a of -10 for those values. Now for part B is a little bit more complicated because I have to do several steps. But if I want to know the speed of impact at point A, remember before we said if we're down here, the speed of impact would be what? It's going to be the same as what we started with, right? But here, that speed is somewhat different. Now, the x component of the velocity is going to be the same as what it is at the beginning, but the y component of the velocity is going to change. So in this part, you have to find first the x component of the velocity over here, recognize that it'll stay the same, and then you have to find the y component of the velocity. So we find vx, and then we also find vy, and then recognize that those are two vectors, and we find the resultant of them, which is going to be v, by using the Pythagorean theorem. All right? So vx is v naught cosine theta. What is vx, somebody? 19. All right. And then vy, well, how do I find vy? Vy changes. How does vy change? What's that? Well, it initially decreases, and then it increases in the negative direction. And we can calculate vy as it changes through time in this way. All right? Does anybody have vy? Anybody get that far for vy? Answers, do you have vy? No. All right, so it's going to be v naught times sine theta. That's 30 sine 50, which is 0.766 minus 10 times 3. Is that right? No, I didn't multiply. I'm sorry. It's 23. It should be 23. Minus 10 times 3, which is 23 minus 30, minus 7 meters per second. Is that right, Josh? Who said no? That's right. Okay, so that's our Vx and our Vy. And so now we have these two vectors, and to find the velocity, we say the square root of 19 squared plus 7 squared. I get 20 meters per second. Okay? Yeah, 20 meters per second. All right. Now, for the last part, I want to know the maximum height above the ground. We've done this problem. All right, it's going to take a couple steps. Does it reach the maximum height at t equals 3 seconds? No. We have to find the time at which it reaches that maximum height. And then once we find that time, we can plug it into the equation for y and find the y position. Gosh, how are we going to find the time for that maximum y position? What do we know about that position that allows us to find the time for it? Right, the v in the y direction goes to 0. So we can go back to this for part C. And we say, we want to know the time right here. My gosh, what is the time? And we scratch our head a little bit, and then we say, oh, Vy is equal to 0. So just like we've done before several times, we say Vy equals V naught y plus Ayt, and we say 0 equals 30 sine of 50 minus 10 times t. And we can solve that for t. Anybody have a t for that? 2.3, is that right? 2.3 seconds. So now you can probably see why I changed the time. Remember, it did say 2 seconds. What would happen if it was at 2 seconds? Where would the projectile be ending? It's 2.3 seconds right here. So would it be to the left or right of that? It would be to the left. So it would be somewhere over here. That's okay. In fact, we could have done that because it wouldn't be a picture. Also, if we did 2 seconds, how would that affect our velocity over here? The velocity in the y direction, particularly. It would be, here it was negative, but if we were over on this side of the maximum height, the velocity in the y direction would be what? It would be upwards, right? It would be positive. Okay? Alright, so we're almost done here. We want to know now what is the height at that point. So just like we did in part A, we can predict the height at that particular point just by saying y equals v naught y times t plus 1/2 ay t squared. That's going to be 30 sine of 50 times 2.3 minus 10 times 2.3 squared. And I get 27 for that. So it goes up to a maximum height of 27 meters. And that also jives with what we know about the other height, because we found in part A that the cliff was 24 meters. So it goes up to 27 meters, and then it drops back down to 24 meters. All right, good example of a test question like this. You can see something like this. We'll do a few more today, sort of as practice for that, or at least one or two more. Yeah, John? Oh, yes, you're right. Thank you. I'll just put in a half here. In my mind, I wrote 5. Okay? This is pretty exciting stuff. And it don't look very exciting, but that's okay. But it is exciting because it allows you to predict the location of objects that are traveling through space and time. And that can be very practical in order to predict where things are going to go or where things are going to be as they travel through space. Okay, let's, I don't think that we've done all the clicker questions for this chapter, have we? Somebody tell me, where did we leave off? And then we'll come back to some more practice problems. Did we finish them all? I'm sorry, can you say it again? 3.3? We did do this one, right? Okay, so small cart. I'm not sure if we did 3.3. We did one very similar to this. We might have skipped it, but the answer is 37. Okay, so 3.4a. We did not do this one. All right, let's try this. A small cart is rolling at a constant velocity on a flat track. It fires the ball straight up into the air as it moves. After it's fired, what happens to the ball? So what's happening here is I have a cart. It has a little cannon in it. It takes a cannonball and it shoots it straight up. And the cart is moving at a constant velocity. So what happens? It fires the ball up. What happens to the ball? Does it depend on how fast the cart is moving? Does it fall behind the cart, in front of the cart, right back into the cart, or does it remain at rest? All right, we'll stop in about 10 seconds. I'll stop at 1:10. You guys are split between two different answers, almost completely split. 1:10. Okay, so most people put B, so a lot of you put D. B is it falls behind the cart, and D is it falls right back into the cart. If we can do this, I can be the cart. I'm going to take this. I'm just going to throw it up as I'm walking along. So I'm going to walk at a constant speed like this, and then I throw it up, and it comes right back down. Because as I'm walking, I'm giving this thing some velocity in the x direction. And that velocity doesn't change as I'm walking. It continues traveling in the x direction. Since I'm traveling at a constant speed, we're both traveling in the same speed in the x direction. And so while the thing goes up, it comes right back down and falls into my hand. So this one is going to be D, that the object will fall right back into the cart. There's a picture on the next slide. All right. Now the cart's being pulled along, same situation, except it's being pulled by a force, and so it's traveling along in an accelerating state. Its velocity is increasing. It fires the ball straight out of the cannon as it moves. After it is fired, what happens to the ball? The track is not tilted, by the way, so you can just disregard it. Does it fall behind, in front of, into the cart, or does it remain at rest? The cannonball, that is. All right, I'm going to stop at 50 seconds. 50. Awesome, you're doing well. Okay, good. B is the right answer. It falls behind the cart. So let's see if I can do this. This is a little harder to do. But when I throw it up in the air, then I speed up. And so if I throw it up in the air, then it just falls behind me. Because I'm speeding up, it still has the same initial x velocity, but then I speed up and I leave it behind because I'm accelerating. All right, you drop a plane, or you drop a package from a plane, flying at constant speed in a straight line. Without air resistance, the package will do what? Will lag behind the plane, remain vertically under the plane, and the head of the plane are not fall at all. Here's my plane. It has a package which it drops. It's traveling in this direction. What happens to the package? All right, I'm going to stop at 55. 55. Okay, good. It's going to remain vertically under the plane. So as it's traveling along, they both have a certain velocity in the x direction that's equal. And so this thing is going to fall like this, but at the same time, the plane is going to continue going at the same speed. This is just like the cannon and the cart, except it's flipped upside down. So the package will continue traveling in the x direction. All right, and then from the same height and the same time, one ball is dropped and another ball is fired horizontally. What happens, or which one will hit the ground first? By the way, I have this here, so this is a device. It allows you to drop a ball. It'll kick this ball out. It'll drop this ball straight down. You push this. It throws one ball out, and then it drops the other ball straight down. So they both travel the same y distance, but which one will hit the ground first? Will it be the one that's dropped, that falls straight down, or the one that's fired horizontally, that goes out, and travels a greater distance than the one that's just dropped? Feel free to ask your neighbors. Please do ask your neighbor what they put. We have about 2/3 of you, one answer, and 1/3 of you with another answer. So just turn around and tell your neighbor what you put. Which one will hit the ground first? All right. All right, I'll stop in just a few seconds at 125. 125. Let's try it. Let's see, I think they're away on the desk. It's going to be kind of loud, okay, so y'all watch out. So you can listen too for the ball, so listen. You can't see well. Or maybe another one on the ground. If you can't see, listen for the ball, see if they hit it at the same time. Yep. So throwing one ball out to the side and dropping another. Sorry. So did they hit it at the same time, or did the fireball hit later? They hit exactly the same time. The reason they hit it exactly the same time is because, well, they fall the same distance. Right, so the answer here is C. In the previous problem, which ball has the greater velocity at ground level? Is it the drop ball, the fired ball? Neither, they both have the same velocity, or does it depend on how hard the ball was thrown, the fired ball? But which one has the greater velocity at ground level? Think about your x and y components. They make up your velocity. And so the velocity when it reaches the ground will be the combination, the vector sum of the x and the y components. And so think about how the x and y components are different for these two different balls, the x and y components of the velocity. Ask your neighbor what they put, please. I'll stop at 1 minute. Tell your neighbor what you put with great confidence. Emma, can you tell Asia too? Asia, tell her what you put. Yeah. Hillary, can you tell Sadie? Okay, I'm going to stop at 1:15. I don't like to talk at 7:30, do you? No, understand. Okay, the fired ball does have the higher velocity because they both have the same Vy. They both have the same y component of the velocity. But the fired ball has that additional x component that the drop ball did not have. Projectile is launched at an angle of 30 degrees. At what point in its trajectory does the projectile have the least speed? If y'all get 80%, I'll tell you a joke. I have a good one for you. It's just right for y'all today. Where does it have the least speed? I'm going to stop at 35. 35. Oh, awesome. Look at that. 97%. Should write a paper about what's the effect of a good joke on performance on a question. Or maybe it was an easy question. Was it an easy question? Okay, so B is right at the highest point in flight because the velocity isn't 0 there, right? It has an x component of the velocity, but the velocity in the y direction is 0. And so that's where it has its least speed. What did the dog say after a long day of work, or school, if you will? Ruff. That's how y'all look this morning. That's okay. I understand. All right. Which of the three punts has the longest hang time? Oh, and here let 1, 2, 3 be A, B, C. So does the first, second, or third, or does the fourth one, do they all have the same hang time? Think about what determines the time that an object is in the air. What have we said that determines the time that an object is in the air? That is the hang time. And that'll give you some clue as to which of these has the longest hang time. All right, I'll stop at 55. 55. Okay, good. D is right. Because what determines the time that an object is in the air? The y motion. Right. So the y motion determines the time it's in the air. So since these all have the same y displacement, they're all in the air for the same amount of time. Now they have different angles and different initial velocities, and that's why they go different distances. But they all have the same hang time. They're all in the air the same amount of time. A battleship simultaneously fires 2 shells at 2 enemy submarines. The shells are launched with the same initial velocity. If the shells follow the trajectory shown, which submarine gets hit first? So this is A. The trajectory follows this path, and it's a closer battleship. And this one is B, and it's further away. Well, I guess it should be like a destroyer or something. Maybe battleships anymore. Which submarine gets hit first? Or do they both get hit at exactly the same time? Remember, what determines the time that an object is in the air? What determines the time? Is it the y motion or is it the x motion? Which is it? What determines the time? Is it x or y? It's the y motion. Tell your neighbor what you put. A lot of you have the wrong answer on this. So tell your neighbor what you put. Okay? Tell your neighbors what you put. Tell your neighbors what you put, John. Tell them after. Yeah, you can just tell them. All right, I'm going to stop at 135. 135. Okay, good. That's awesome. You got a big swing there. Let's see. Did I tell you about when the police came to my house? Oh, shoot. If a cow wants to add 2 numbers, what does it use? A calculator. That was pretty funny. All right. For a cannon on Earth, the cannonball would follow path 2, or we'll call it B. It would follow this path. On the moon, where the acceleration due to gravity is 1/6 what it is on the Earth, 1.6 meters per second squared, which path would the cannonball take? Would it take one? Would it take the same path, a slightly different path, or D? All right, we'll stop at 50. Is D right? Hey, D is right. That's awesome. So the y motion, the y acceleration is decreased, so it takes less time to fall. Excuse me, it takes more time to fall. So that's going to allow it to travel out at a farther distance. Because the acceleration is less, it's just going to require more time to fall. That's why when you see, like, Neil Armstrong on the moon, he jumps up and down, it looks like he's sort of floating. And it's just because the acceleration is less, and that causes it to appear like he's in the air longer than he should be. And he is in the air longer than he should be than we would expect on the Earth. All right. Oh, two snowmen were out in the field, and one looks to the other snowman and says, "Funny, I smell carrots too," because they have carrot noses. Yeah. Okay. All right. Let's go. Spring-loaded gun can launch projectiles at different angles at the same launch speed. At what angle should the projectile be launched in order to travel the greatest distance? And we will stop at 30. Stop at 30. Have to get 100% on this. Okay, awesome. C is the right answer. 45 degrees gives us that maximum range. And listen, it gives us maximum range. We said before that it maximizes your time in the air and it maximizes your velocity in the x direction. That's not exactly true, because to maximize our time in the air, we would have it go up with just y component of velocity, and then it would go up really high, but then it would come down really low. To maximize the Vx, we would give it just velocity in the x direction. But then it wouldn't have any time in the air, and it would just drop down right there. So in between those two, when we have 45 degrees, it doesn't have the maximum Vx, and it doesn't, nor does it have the maximum time. But it has those values that are maximized so that it does give you the maximum range. Okay? So 45 degrees is the right answer. Oh, and let's see. I was wondering why the baseball was getting closer, or why it was getting bigger, and then it hit. All right. Let's say you're trying to hit a friend with a water balloon. He's sitting in the window of the dorm room directly across the street. You aim straight at him and shoot. Just when you shoot, he falls out of the window. Does the water balloon hit him? You're going to assume that the shot does have enough velocity to reach the dorm. So your friend is here, you're over here, and you aim directly across the street at him. But just as you shoot the water balloon, he jumps out of the window. What happens? This happened just last night. I was trying to shoot somebody across the street with a water balloon. And they jumped out of the window.
There's a pause in there.
Alright, does the water balloon hit? Okay, we'll stop at 105. 105. Okay, yes, it is going to hit. What's going to happen here is that when you shoot your balloon straight across, it's going to start here, but it's going to fall at the acceleration due to gravity. And in that same amount of time, your friend is also going to fall so that they will meet right there. Now, if your friend didn't jump out of the window, how should you shoot your water balloon? You should shoot it at an angle so it will go up and then come back and reach the window. But if you know that he's going to jump out of the window at the same instant that you shoot your water balloon, then you just shoot it straight across. This next one's similar. We're going to skip it, but it's the same idea that when I shoot the water balloon, it falls like this, and your friend will similarly fall at the same distance, or at the same rate. All right, let's do a problem. in your supplemental problems. That's at the back of your homework. Listen, guys, to prepare for the exam, you should work through the homework. There's some good vector problems and some good projectile motion problems. There's also some supplemental problems here that we're going to work out in class. We might not work them all, but we'll do this one at least. So here a soccer player kicks the ball from a distance of 30 meters towards the goal. And I want to find the initial speed of the ball as it passes over the goal just 2.4 meters above the ground. The initial direction is 40 degrees from the horizontal. So whenever I encounter a problem, I always like to draw a picture. It helps me to sort of keep track of what I know and what I don't know, and just get an idea about what the situation is. So first of all, I know that I have a ball, and I know that I have a soccer goal over here. I know that I kick the ball at an angle of 40 degrees. I don't know V naught, but I want to know what V naught is. So I want to find the initial speed. And I know that it passes over the goal 2.4 meters above the ground. So it comes over here, and it hits the goal there, or it passes just over the goal, when the distance here is 2.4 meters above the ground. And I also know another thing about that point, is that the distance from the goal to the ball is 30 meters. Alright? So what I'm going to write is, I'm just going to write over to the side now everything that I know about this situation. I know the angle. I know theta equals 40. I know the x displacement is 30 meters. And I know the y displacement is 2.4 meters. Both of these at some time. I'll just call it t. But I don't know what that t is. So remember, when we're talking about projectile motion, there's not just a single time. There's times throughout the trajectory. And in this particular case, I know the exact position of this object at that time. At that particular time, which I'm just going to call t. I know my accelerations. I know ax, ay. Ay is equal to negative 10 meters per second squared. Okay, I'm going to write down my equations here. X equals vxt. Y equals v naught y. T plus 1/2 ay t squared. And then vy equals v naught y plus ay times t. So this is where I would start for every problem. I'll draw a little picture, I'll write down everything that I know, and then I'll try to figure out what is it that I don't know. I don't know the time, and I also don't know V naught. And I want to know V naught. Okay? Now I have my equation, my kinematics equations. I can go through, and first I want to know this, or this. Actually, I don't really want to know V naught y. I just want to know V naught. But since I know theta, then if I find V naught y, then I can find V naught. You with me? All right. Now I'm going to underline the things that I don't know. I know x. I don't know vx, and I don't know t. I know y. I don't know v naught y, and I don't know t. I don't know t. I know I don't know vy. I don't know v naught y, and I don't know t. All right. So notice here, these top two equations, I have two unknowns, and I have two equations. So I can solve these equations simultaneously to figure out what is V naught. Now you might say, well, really I have three unknowns. Is that what you're thinking? Because I have Vx and V naught y. But remember, these are embedded. This is actually V naught cosine theta, and this is v naught sine theta. But since I know theta, then both of these unknowns are dependent upon v naught. So I have two equations, two unknowns. I can solve them simultaneously. So let's write them. And for the next exam, you will likely have to solve a system of two equations. Did you have to do that for the previous exam? You did. All right, we'll see. You may or may not have to, but you should be prepared. Definitely when we get into chapter 4, you'll need to solve a system of two equations, and we'll do that in more detail. But you could see it on this next exam as well. I'm going to take these two equations. I'm going to leave that third equation because there are three unknowns, and so it doesn't really help me in solving this. And I have two equations with two unknowns already. So let's just write them a little bit differently. I'm going to say y equals v naught sine theta t minus 5t squared. And then I have x equals v naught cosine theta times t. I'm going to solve this equation for v naught, and I'll get v naught equals x over cosine theta times t. And then I'm going to take this, I'm going to plug it in for v naught. So now if I do that, I get y equals x over cosine theta times t times sine theta times t minus 5t squared. I got that minus 5 because it's 1/2 of a. Okay? I can simplify this a little bit. And in fact, I wrote it this way. That is, I solved that second equation for v naught because it helps me to get rid of one of my t's, and it just makes it a lot easier to solve. So here, if I get rid of my t's here, and if you like, I can change my sine over cosine. Gosh, what is sine over cosine? Do y'all remember how it's related to tangent or cotangent? It's tangent. That's good. So I have here x tan of 40, my angle 40 degrees. Yeah, x tan of 40 minus 5t squared is equal to y, and y was equal to 2.4. So now I can solve this for an x here is equal to 30, because I know that that value is given. I can solve this for t, and I find that t is equal to 2.13 seconds. Now that I know t, it becomes fairly trivial. I can just take this. I already have an expression for v naught, and I plug it in there. And so I say v naught equals 30 divided by cosine of 40 times my t, which is 2.13 seconds. And that works out to be 18 meters per second. All right? Every problem that you approach, you'll approach in this same way. You'll write down what you know, write down what you don't know, draw a picture if it helps you. Eventually you might get good enough that you don't need to draw a picture, but I still like to draw pictures. It helps me to think about what's going on in the problem. And then you try to develop an approach to solve the problem mathematically through algebra. In this case, it was not trivial because you have to solve these two equations simultaneously. All right. We have a few minutes left. I want to just set up problem number 3. Problem number 2, I'm not going to work in class because it's basically the same as problems that we've worked before, but I want you to try it on your own. It is good practice for the exam. Problem 3 is a little bit different because you have to use the quadratic equation to solve it. So problem 3, I have an object that comes over here, but it lands at a distance below where it hits. In fact, there's like a volcano, and it lands at 5 meters below where it begins. So my y displacement is equal to -5 meters. I know a lot about what happens it has a certain angle, 23.57 degrees, and I give the velocity to it's 25 meters per second. And so I know a lot about this and what it's doing, but I want to know what is t over here. We can take this equation, y equals v naught y times t plus 1/2 ay t squared. And I know y, I know v naught y, because it's just this times sine of this. I don't know t, I know ay, and I do know t squared. So I can put in the values for all those, and I'll go ahead and do it. I get y is -5. V naught y it turns out to be 10 meters per second times t minus 5 t squared. Y'all know how to solve a quadratic equation? Just step through it quickly. We have a couple minutes. So I set it up like this. I write it as 5t squared minus 10t minus 5 equals 0. And so this becomes a, this becomes b, and this becomes c. And then I give you this. T is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic equation. You probably know it. If you don't, I'll give it to you if you need it on the exam. I'll write it on the board or whatever. If I solve that, I get two answers. Because I have this plus or minus here, I get t is either equal to 2.4 or it's equal to minus 0.4. Which of those would be my time? 2.4. The negative 0.4 goes away because you can't have a negative time. Sometimes you have two physical answers. In this case, you have one physical answer and one that just doesn't make any sense. All right? I might come back and finish this, but I just wanted to show you that sometimes you just have to use the quadratic, especially if your v naught y is 0 or is not 0 and your y value is not 0. Look back at those supplemental problems and the homework problems. They're there for practice for you to finish this chapter, but we will definitely move on to chapter 4. If you have questions about chapter 3, you can address those on Monday. The test is coming up, okay? It's not the 5th of October, yeah. It'll definitely all just 3 or 4. Maybe some 4 in chapter 4, but only the first 4.